Alright, today we'll be looking at 1.5 and 1.6, which is atomic structures and electrons and PES. Let's just start with the atomic structure. So basically we're looking at the atom, an atom with basically a nucleus that contains neutrons and protons surrounded by a cloud of electrons. It's the basic structure of an atom, right? Protons and neutrons, they're around the same size and mass, and they make up the nucleus of the atom. They also make up most of the weight of the atom, while an electron, although negatively charged, does not contain significant mass, so we don't calculate for the mass of that. Um, so basically, when we're looking at electrons, they are held in shells, is what we call them. Basically, rings around the nucleus, and then each one of those shells will contain a sublevel, S, P, D, F, and orbitals. And an orbital is just the region of space that the sublevel actually contains within the shell, and most of these is probably detailed more later on inside the course. But what is important is electron configuration. Basically, let me pull up the periodic table here. Um, so, okay, say we have a periodic table here. Basically, the first level is 1, second level is 2, third level is 3. This should be taught in general chemistry, so if you want to review, there's probably other videos on that, so I won't go into much detail here, just because it's something that should have been taught before. And then probably your sublevels you might need to remember. If I draw the periodic table as best I can here, right? We have helium, so this is included in this. I can change different colors for this. Is the S subshell. This is also the S subshell, while let's say the transition metals is D subshell, and this last part is the P subshell. And there is the F block, which is the ones that are contained below the periodic table, but that is commonly not asked. That I don't think it's part of the AP Chem curriculum. So the ones that you do need to remember is S, D, and P, and also remember that because of the energy difference of the D subshell, the D's come after, right? This D is 3D because it is before the 4S here. It is less in energy. So just keep in mind that it goes 1 and then 2 and then 3. And then this is 3 while this is 4. So 4S and 3D are on the same level. So consider that when they're asking, for example, a question on the valence electron configuration. Just keep in mind that this 3D subshell is before the 4S and 4Ps. And for orbitals, right, it's literally just a region of where the electrons will be within a subshell. And that's where the S, P, and D come from. Those are orbitals. It's just the area where the electrons could be. The S holds 2 electrons, the P holds 6 electrons, and the D holds 10 electrons. Um, and I don't think the shapes are important, but the S, easy to remember, it is spherical, so sphere. The P is kind of like a peanut, looks like a peanut, and then the D is a double peanut, which is probably easy to remember. D is a double peanut. Those are the shapes of each subshell. Next, electron configuration rules. Now, there's 3 principles just to keep in the back of your mind. Most of them make sense, but the names you might forget. We have the Aufbau's principle. Basically, you're building up from the lowest energy to the highest energy. That's pretty obvious. You always want to start with the lowest energy orbital first. Why would you want to go to the highest energy initially? Doesn't make sense, right? Pauli's exclusion principle, basically only 2 electrons per orbital with opposite spins. Opposite spins means one goes this way, one goes this way to counteract each other. That's, you know, based, and then one part only holds 2 of them because that's the most stable. That's what we call Pauli's exclusion principle. And we have Hunz's rule, which basically says, they always want, say we have the D subshell, it holds 1, 2, 3, 4, 5. You always want to fill every single spot first before we hold the other ones, just because that'll make it more stable. Why would you want 2 electrons to be counteracting each other when you can all have them in different spots? You want to fill them up first for them to be the most stable. Next, valence electrons, right? I mentioned valence electrons before. They're basically every outer electron. So for example, if we have like an atom here, the valence electron would be these outer electrons that are held. And okay, so transition metals technically only have 2 electrons, but the inner d electrons can be lost during ion formation. So say titanium, which is 4s2 and 3d2, can lose 2, which will knock this off, or it can lose 3 or 4, which is knocking more out of the D subshell, because it can also take, when it's being ionized, it can also take electrons out of the D subshell. Next, okay, ground and excited states. Basically, a ground state is just the lowest energy state of an atom, meaning all the electrons are at its lowest state. And an excited state is basically when you shoot a photon, when you shoot a photon at an atom, you send energy to it, right? And when you send energy to it, it becomes excited. And then let me just draw a diagram here. Say we have an electron here. You shoot a little photon ray at it, and the electron, what will happen is the electron would jump to an outer subshell, right? It'll jump to an outer subshell, or outer shell. It'll jump to an outer shell when it's excited because of the energy you shoot at it. And then eventually it can't be there forever because you're not constantly giving it energy. It'll jump back down to its lower shell. And basically what happens is when it jumps down, it'll emit a photon or a light back to us. And that continues on to where light comes in, where light and energy comes in. Basically, how much energy you shoot at it, when it falls back down, it'll emit that energy back to you. And that energy is equal to our equation equals H times V. And then that's where, when we see color, when we see visible color, that's where the color comes in. So, okay, so there's 2 equations that are given on the formula sheet, E equals HV and also C is equal to lambda V. And they're pretty simple to use, right? Energy is equal to, was it Planck's constant times frequency, and then speed of light is equal to wavelength times frequency. And to connect those two, they both have frequency in it, so it's just simple algebra. Once they give you a number, you just plug it in, but make sure that wavelength is in meters, because that's what they wanted in. And another cool trick is if you ever forget what unit they should be in, look at the constant. So for example, if we look at E equals H times V, right? Actually, we'll do C is equal to lambda times V, right? So C is equal to 2.998 times 10 to the 8, but what we're looking at is meters per second. Notice how it's meters. That means that lambda here, or that lambda, which is wavelength, that means that lambda has to be in meters to match the same unit that the speed of light's in. So just, that's a cool trick whenever you forget what unit it's supposed to be in. Last one, Coulomb's law, right? So Coulomb's law, it's given by like it's given by like something similar to Newton's law of gravitational pull, or gravitational whatever. But this doesn't actually matter, right? You don't actually need to know this formula. All it says is that forces of attract. It's basically the bigger the smaller the radius and the bigger the charge, the bigger the attraction between the two. So if you have bigger charges between two atoms and there's a smaller radius between the two, they'll have bigger charges. And that is used when you're trying to find atomic trends, like say which one would have stronger like intramolecular forces or whatever. They love seeing Coulomb's law be used when you say like, oh, because both have smaller radiuses or both have bigger charges, they're gonna be more attracted to each other. That's kind of the way I would put a lot of these. So just Coulomb's law is very important when explaining a lot of these reasonings. And charges is just, say, when they're ionizing, like if you look at the periodic table, how many electrons you need to form that 8 valence electrons. It's just what charge it'll be when it ionizes. So for example, sodium would have +1, like chloride would have -1. They both have +1 and -1. While if I give you like magnesium, which is +2, and oxygen, which is -2, these would have oxygen, which have -2, these would have bigger charges. So they would have stronger attraction towards each other. So a PES, it's not very important how the system actually works. It's more of analyzing the graph. And the graph is given by, basically it'll have binding energies, and relative in number of electrons, right? I'll just do number of electrons. And basically what it'll have 0 here. So actually there's not an arrow, but sorry. There's 0 here, and then say it's like 90 here, right? And it'll have these little bumps showing the energy that the electron sends out. And basically what happens is when you're given one of these, this bump would have, or this little spike would have the most energy, while this spike would have the least energy. So if it has the biggest binding energies, that means this is your highest binding energy, which is 1s, because it starts at 1s. And then this would be, because it's the closest to the electron is the closest to the proton, so that bonding energy would be the strongest, binding energy would be the strongest. Then this would be your 2s, this would be your 2p. And that makes sense because there's more electrons in the p subshell than in the s subshell. So that's how, if you're given like what element is this, well, if this is 2 electrons, 6 electrons, that would be neon, right? 2s, and then 1s, 2s, and then 2p. Okay, that should be pretty much it for 1.5 and 1.6. I would just say remember how to use these light equations, and PESs should be generally pretty easy to remember. Same with Coulomb's law, it should make sense. So yeah, on to the next one.